faire tourner ça avec ça?
C'est ça. Avancer, reculer. Et ça, il a dit, il faut bien garder proche.
Okay. Hello. Good afternoon, everybody. So I will start the presentation. Today we will speak about a technical topic that concerns containment leak-tightness verification, and especially dedicated for SMRs and AMRs. I will do this presentation together with my colleague Masa Moussayan. Gianni Odassa, I present myself. I am the director of the civil engineering department in Clermont-Ferrand for INGEROP. And Masa, perhaps you can present.
Yes, and Massa, I'm responsible of the department of scientific calculation for Ingérop in Paris.
So I will start with a short presentation about Ingérop, in case everybody doesn't know our engineering group. So the engineering group, Ingérop, studies these 7 different types of activities that goes from buildings, water, energy, industry, infrastructure, transportation, and urban development. And our services go from all type of design, from feasibility studies till construction, passing through detailed design. We are located mainly in France. Our headquarters are in Paris, but we have offices all around France in the most important cities as Bordeaux, Lyon, Marseille, Lille, and my office that is in Clermont-Ferrand. We also have a lot of subsidiaries outside France. Our most important subsidiaries are in the UK and in Germany, but we are located in all the continents in America, Africa, Oceania, and Asia. Just a few numbers that are key from our group. Here you can see the evolution of our turnover, that it's quite positive in the latest year and basically very linear. So we can see here that we have passed in 2021 from 274 millions up to 458 millions of euros of turnover, and that our activity is spread mainly in France, but we also have a very important part of it that occurs abroad, 31%. In terms of the breakdown of our activity per type of design, main part it's distributed in infrastructure, mobility, and building. But for the part that concerns us today, which is energy, we have more or less 10% of our turnover that it's dedicated to this domain. In terms of order book, we usually have around 18 months of order book of activities in front of us all the time. And in terms of resources, we are 3,500 people around the world and 2,500 in France. If we speak a little bit about the energy field, we mainly work in nuclear activities, but not only. We also work in hydrogen and decarbonization, photovoltaic, geothermal energy, heating networks, smart grids, and interconnections, water recovery for energy production, and biomass. Finally, if we just give a presentation of the different technical actual disciplines that we work on, for the nuclear activities, we basically give technical support for project management, fluids and electricity and HVAC, climatic engineering, health and safety, nuclear safety, process and layout, and in architecture, and civil engineering that goes from geotechnics passing through structural engineering up to facades. In terms of certifications, we have several that allows us to work in the nuclear environment, and I can highlight especially the certification ISO 19443 that we have obtained since at least 3 years. Finally, if I start speaking about the actual technical topic that we want to discuss today, so it's about how we are going to substantiate containment in reactor buildings that are not lined, that doesn't use steel liner. So if I start just with the basic principle, in a nuclear plant, we usually provide the substantiation of containment following the 3 barriers principle. First barrier, it's actually ensured by the fuel rods that we can see here in the vessel. Then we have a second barrier that is the reactor cooling boundary. And then the third barrier, that is the one that we want to present today, is the civil engineering structures that is supposed to be very robust. That is the one that prevents any release of radioactive materials to the environment. It needs to be very airtight, and it needs to be to have a containment capacity. For the reactors that we have in France, we have two main types of third barriers. And I have an example here in the right, which is a single shell containment reactor that is basically composed by reinforced concrete structures with prestressed concrete and with a steel liner in the interior part that we can see here. This type of system, that is the one that is, for instance, actually used on EPR2, ensures that we will have typically in between 0.25 to 0.5 overall leakage of the contained mass of gas per day. So that's an important value that we will need to keep in mind for the rest of the presentation. And typically, if we remove the liner, but we keep a reinforced concrete structure with prestress, we can obtain a leak rate that goes from 1 to 1.5 overall leakage of the contained mass per day. So how it actually works? In principle, it's quite simple. So we have the reactor containment, and then we will have two types of leakages. The first one is the one that passes through the openings, and that is usually the most important. And there are several different dispositions that we can have to ensure leak tightness through the openings of a reactor, and there are quite a lot. And the second one, that is the one that we want to study and present today, concerns the leakage that passes through the structure, the concrete structure. This leakage occurs in two scenarios. The first one is the normal situation, which is actually when the nuclear plant is working in normal situation. And the second one is the one under accidental situation, and the one that we study the most is the one under severe accident, when we have a violent increase of temperature and pressure. In France, and most of the safety authorities of the world, required to have a containment principle that it's capable of ensuring the leakage below the required design values. This value varies depending on the country and on the type of nuclear plant, in between 0.15 to 10% of the contained mass of the gas per day. In some cases, we can exceed this value, but only when we are totally capable of estimating with experience what it will be the complementary leakage that we will have. Here we can see some examples of containment of different plants around the world. The first one that we can see in the top left part over there, it's a single wall containment with prestressed concrete and liner, so similar to the one that we have, for instance, for EPR2. The second one, it's a double wall containment with prestressed concrete and without a liner. We have some of the old reactors in France that have been designed like this. And the last one that we can see is a double wall containment with prestressed concrete and liner, and it's really similar to the one that we have for the EPR, for instance, in Flamanville. Why we have different design solutions? Why it's not always the same? The response to that is that we are, at the end of the day, when we are designing a containment system, is to ensure nuclear safety. That's the first basis. But the second one is that we will always be looking for improvement in cost and time of construction. We can see that even the EPR2 in France has removed one of the containment walls in order to optimize a little bit the duration and the cost of the construction. And for the SMRs and AMRs, this is a real question, because we need to be sure that we are designing something that is going to be safe first, but also very interesting in terms of cost and time of construction. So once we have said that, it's important to remind what the applicable codes that we have actually, especially in France, propose in order to design a containment. Basically, the containment substantiation will be based on the material properties. It can be steel liner, or concrete reinforced or prestressed. However, when we really analyze deep the containment principles, we need to get out only of the mechanical parameters of the materials, and this is a part of the presentation that my colleague Massa will show after. Today in France, the most used code for the design of containment of reactors on civil engineering is the LCC CW 2023. This code is really clear in terms of what is the domain of application or applicability that we have. It's written at the beginning of the code that it's only valid for a single wall prestressed concrete with a metal liner, or a prestressed concrete with a metal liner or inner surface, and where the outer wall is reinforced concrete. This code applies to nuclear power plants with a reactor building containment, including a steel liner. That's what we need to remind. It is not applicable for containments without it. So if we continue with this, for reinforced concrete containments without a liner, the applicable codes only provide criteria for substantiating containment based on crack control and stress limitation, but they never ever address an estimation of the actual potential leak rate that we will have in a structure of concrete when it's subjected to an important value of temperature and pressure. This implies that applicable codes today do not furnish any substantiation for the criteria of the leak rate assessment. And this is the question that we ask to ourselves today, how we can substantiate this in a reliable way. And Massa will continue with the rest of the presentation.
Thank you, Janio. So here I will present you the methodology and software that developed in Ingérop in order to study, by modeling, numerical modeling, study the leakage tightness degradation of this type of structures, the containment structures. So what was our objective? Our objective was to develop a simulation tools in order to predict aging and leak tightness degradation of a containment structures. And what were our application areas? It was we want to help the operators to predict the service life of their structures. We want also to prepare the future reinforcements. This tools help us to do several safety studies. And it also helps us to understand the in situ measurements when there are the structures which are already in life, and we want to study, and they are instrumented, and we want to understand their the measures. So when we developed our tool, we had some a specific framework. Our framework was, firstly, we wanted to have a tool which represent a complete solution. It means that all important physical phenomena are integrated in our model, and we wanted we wanted this tool to be applicable to industrial size structures. We don't want a very complicated thermo-hydro-mechanical model which is not applicable to structures, but a tool which is in terms of cost and in terms of ease of use is applicable to these types of structures. We want, for sure, we want a reliable method. It means that we don't have lots of standards and code, but we want to be able to validate all our results with experimental data, and also we want it to be, for sure, numerically robust. So that was the framework of our work. And so in our, what was the main physical phenomena of the loss of permeability of concrete is that concrete, as you know, is a porous multi-phase area. So there are pore networks in concrete which can be filled by gas or water. So it's unsaturated. So concrete has already its intrinsic permeability and porosity. It is impermeable. But what is important to know is that the permeability of concrete can evolve in time by cracking of concrete, so the aging and degradation of concrete, but not only, also by drying of concrete. Drier concrete is more permeability is. That's why they are, the key factor influencing on concrete permeability are porosity, intrinsic porosity of concrete, but water content, drying of concrete, and also cracking of concrete. So these parameters should be studied in our structures. In industrial structures, but all structures, during all whole life of structure, there are several loads which are applied to our structures. In early age, we have hydration, autogenous shrinkage, we have creep and cracking, and then if the structure is prestressed, we have prestressing loads, we have weights of the structures, and then so on, we have drying of the structures during the lifetime. Here, I present a case of, for example, a reactor containment building, which is built for a lifetime of 50 years. So during 50 years, there are different loads, which are the nature of thermo-hydro-mechanical loads, which are applied on the structures. So, given that, we classify the leakage which passed through the containment vessel into 3 different parts. The first part is the gas flow passing through the porosity, natural porosity of concrete, okay? The second one is the gas passing through the microcracks. What I call microcracks are the cracks which are not visible, but we see that the concrete is degraded and it's dried, it's a dried concrete. And the third one, the last one, which is the most important part, it is the gas passing through the macro cracks. Given this, so if we have thermal states, hydric states, and mechanical states of concrete, we can solve hydric equations and we can obtain the global gas flow passing the structure. Okay, here I will just show you the chart which summarize different calculations that we do in our software. So we do, in order to obtain finally our final results, a leakage of gas passing through concrete. So we do thermal calculations, we do mechanical calculation. Using that, we obtain water degree of saturation. It means drying of concrete. We obtain cracking, and then using that, we obtain the permeability, evolved permeability of concrete, and we obtain the gas flow. This tool we have implemented so in internal software in Ingérop using Codaster, which is EDF finite element code. So now, in order to apply this method, this tool in structures such as double wall nuclear power plants or SMR structures, we need firstly to have the loads applied on the structures. Okay, these loads, either the operators give us the loads, detailed loads. It means thermal loads, pre-stressing loads if the structure is pre-stressed, or pressure loads. Even if we don't have this information, we use codes and laboratory tests in order to obtain these data. For SMRs, sometimes we are in feasibility studies, so we don't have lots of information about loads, so we can obtain them from different type of these loads that I have listed here: mechanical loads, thermal loads, drying load, and hydraulic load. Using some standards or some input data which come from laboratory tests, we can also have operators' values. Once we have input data, we need material data. This is the same way. Material data is, if in very preliminary studies, such as the study that we have done for one SMR, sometimes we don't have the very exact information about the material parameters. In this case, using the concrete class, we can obtain the parameters that we need. Because we need lots of parameters, as we are doing a thermo-hydro-mechanical model, we need mechanical properties of concrete, thermal properties, transport properties of concrete. So in the same way, sometimes we have this information, but if we don't have, we can use laboratory tests or concrete class in order to obtain these values. And then, once we have loading and input parameters, we need to calibrate our different behavior law, which are in our model. So we have several laws, mechanical laws, drawing law, and hydraulic law that we should calibrate it. Here you see different behavior law for modeling, for example, basic creep, drying creep, and so on. So the calibration is very important because this calibration guide the results and the cracking results. So here, in the same way, we have two methods for calibration. The first one that we use for basic method that we use for preliminary analysis or feasibility analysis, in which we calibrate our parameters with the curves that comes from the reference codes, such as ETCCC, or from regularity reference code, the regularity documents, or some laboratory tests. We calibrate our models, and we run the calculation, and we give, as a result, a leakage which passed through the concrete wall. But if we are in the phase which are more advanced of the project, we can do a more refined and optimized calibration, which help us to have more exact results. It means that if, for example, we have I give you one example, in double wall concrete containment vessels, EDF vessels, we have several, it is highly instrumented, so we have strain evolution of concrete, so we can use this measurement in order to minimize, and we do a minimize algorithm in order to obtain the more exact parameters which give us the results which are more realistic. So, if I summarize, we developed a method, a model, tool, in order to calculate and obtain leak tightness evolution of concrete structures. For that, we need input data, which are for sure plan and layout drawings, but also the loads. We need also to fix our standards. And then finally, we obtain the post-processing that we have developed also in home in order to obtain leakage of concrete. If I focus to the results, here I will present the results that we had in our recent study for SMR structure. What the important and interesting results is that cracking, as I told before, it's a very important parameter which impacts leakage of concrete, and drying also. And what we saw is that high temperature can lead to very macro crackings, so that can impact a lot the leakage of concrete structures. Concrete formulation is very important, reinforcement ratio 2, because it impacts the cracking of concrete. The SMR are usually, they don't have a cylindrical geometries, so it's not very well because they are stress concentrations, and so there are leakage in these structures. And also the other problem is that the SMRs are not, some of them are not prestressed, and this also presents a problem because we don't have a compressor state in concrete, so cracking is easier. So that's why it's very important to do these types of studies and modeling in order to be sure that the safety is ensured. As a conclusion, we have a need. Our need is that we don't have any regulation for SMRs in order to study leakage of them. And we need, as SMRs are innovative designs, we need some models in order to represent their behavior. So numerical simulations are needed. Okay, so based on that, we need to have a modeling approach. In our approach, we have a uncoupled thermo-hydro-mechanical models in which is adapted for big size structures in terms of cost and in terms of it's robust, and it lets us to do several sensitivity analysis, safety analysis, and it helps us also to do optimization of the structures. The interesting results and outcomes is that it enhances the nuclear safety, because we can do several safety analysis, so that we can say that it improves structural reliability, and it can also improve the long-term confidence on these types of structures by modeling. Thank you, everyone. If you have any questions.